today. I'm very glad to be able to announce Robert Gramacy. He's professor of statistics in the College of Science at Virginia Polytechnic and State University. And I digged a bit in his web page and found a very interesting research proposal, which I would like to read. I'm a computational statistician. I specialize in areas of real data analysis in the physical, engineering, and biological sciences, where the ideal modeling apparatus is impractical or where the current solutions are inefficient and thus skimp on fidelity. That often requires new models, new methods, and new algorithms. My goal is to be impactful in all three areas while remaining grounded in the needs of a motivating application. I aim to release general purpose software for consumption by the scientific community at large, not only other statisticians. And this is quite nice to read and remarkable, and I think we will get some impression now with the presentation. Please go ahead.
Thank you very much for the really nice introduction, and thank you to the organizers and to David for inviting me. And I have to say I've been very impressed by this meeting, although I'm sure most of us look forward to in-person meetings again sometime soon. I think this has been a great success under the circumstances. All right, so I'm going to tell you about some recent research that I've done on computer simulation experiments. So a computer experiment is a function implemented as a computer code at great expense that simulates some physical or real world relationship. Some great contemporary examples of computer simulators come from epidemiology, so simulating how a disease might propagate through a social network and how intervention strategies like social distancing and masks might impact the spread of the disease. And another one comes from aeronautics or rocket science, simulating how rocket boosters experience forces as they re-enter the atmosphere so they can land ultimately upright on a platform in the middle of the ocean. Both of those examples are situations where the experimentation that's done is almost exclusively simulation based because it's either expensive or unethical to get the kind of data that you would want in the real world. These computer codes, both for epidemiology and for aeronautics, are computationally expensive. They require supercomputers, and even when they're run in supercomputers, they take hours. So it makes sense to plan an experiment to decide what input configurations X you want to put into the simulator, and then get the outputs Y, and then make a map between X's and Y's. So you want to do a regression at the end of the day. Now these computer codes are highly nonlinear. They give nonlinear response surfaces. So we want to think about that when it comes to choosing appropriate models. What would you do with a fitted regression? You would use it as a surrogate for the real simulator. So you could entertain what ifs or perform sensitivity analyses to figure out which variables matter. Or you may want to optimize something to find settings of the inputs that minimize the outputs or something like that. The Gaussian process has emerged as a canonical model for these surrogates, or sometimes people use the word emulator, but just think regression fit to these XY pairs. And the reason for that is because they're nice nonlinear models that give accurate predictions and have appropriate coverage. And also they can interpolate. Historically, these simulators were deterministic, so it was very important to connect the dots between runs. But actually what I'm going to talk to you about today involves stochastic simulation, because most simulators, even for aeronautics and for epidemiology, are stochastic these days, or agent-based models are really common, and we want to talk about how to address that. But before we do that, I want to do some review. This is a plenary talk. I think one of my jobs in that is to give some background and try not to lose people in the first 10 slides. So let me tell you about what a Gaussian process is. And hopefully you'll be able to appreciate why it's popular for modeling simulation experiments. So first I'm going to talk about a Gaussian process prior. Gaussian processes, or multivariate normal distributions in general, can be used to generate random functions in the following way. So take a bunch of X values in the input space. Think of a grid in one dimension or something like that, where you spread out some inputs. and then calculate pairwise distances between those inputs x, and inverse exponentiate them. So I'm going to build a covariance matrix composed of pairs of xi's and xj's, where the values are e to the minus Euclidean distance between xi and xj. I'm going to put that covariance matrix into my favorite multivariate normal generator and take those y values and plot the y's in the xy plane along with those x's. So there's a mathematical description of that at the top here, and there's some R code that implements that scheme. This is a talk in R Markdown. It's fully reproducible. I really liked the session on Wednesday on reproducibility. It's great to see new tools coming online to make this easier. So I'm going to generate 3 sets of y values here with that distance-based covariance structure and plot them for you. So here's 3 random functions generated from a multivariate normal with a distance-based covariance structure. So people would say this is a 3 draws from a Gaussian process prior. Of course, we're not in the business of generating random functions. I'm sure you could find a use for that, but it's not going to be important to us at the moment. What we want to solve is the inverse problem. Given some pairs of data examples, some input-output pairs, we want to know what random function realizations could explain that data. So we want to know about the conditional distribution for y given the data dn. Okay, there's a Bayesian perspective to all of this, but the Bayesian perspective is not super important. What is important are rules for multivariate normal conditioning. And this is why Gaussians are so important, because this very simple Wikipedia result, or one that you probably find in an appendix for almost all graduate level texts, is the following. If you have a random vector x that you've partitioned into 2 groups, you can look at the distribution of one element of the partition given the other. And there's a simple linear equation for how the mean and covariance get updated, say for x1 here given x2. So those formulas are at the bottom, and I won't dwell on them. You can find them on Wikipedia or in a textbook. So I'm going to apply that result in the context of this distance-based correlation structure. So if I want to make a prediction for a bunch of x values, here I'm notating that as curly x, I just need to apply those equations using my distance-based covariance structure. And one thing that maybe I should have mentioned a while back is I'm only caring about the covariance here. The mean is 0. It doesn't need to be 0, but it's remarkable how well things work with Gaussian processes whose multivariate normals have 0 means. So these equations, the application of that Wikipedia result with distance-based correlation, is sometimes called the Kriging equations. That's what they call it in the geostatistics literature. In the computer experiments literature, we like to emphasize that this predictor is a best linear unbiased predictor. So it gets used in geostats and in computer experiments, and finally it's popular in machine learning. So there's a bunch of different areas where this idea is producing some of the best predictors around. So I'm going to code that up for you. Let's create some simple training data for the purpose of illustration. So my training data is going to come from a computer code, and that computer code is the sine function. So that's a very simple computer simulation. So I'm going to observe y of x at 8 evenly spaced x's, and then calculate pairwise distances between them, and then exponentiate them, or e to the minus those distances. I have to add a little small number to the diagonal to keep the matrix from being poorly conditioned, but mostly it's e to the minus distance. And then I need to calculate the same thing for the predictive grid, because ultimately it's going to be the distances between the predictive locations and the training data locations that drive the functions that go through these data. So I'm not going to go through line by line the code. The point of the code isn't really to follow it. It's just to know that it's there and that what you see is what you get. And I feel the same way about the math. There'll be some math later in the slides, and we're not going to go through it in any detail, but it's just supposed to be comforting to know that it's there. All right, so I'm going to follow those conditioning formulas. I'm going to calculate my updated mean and covariance after conditioning on the training data examples, and get a predictive mean and predictive covariance matrix. and then draw random functions from that updated Gaussian process posterior, if you will. And I'm going to plot that for you in the XY plane. So here it is on the next slide. So each of the gray lines in this slide is a draw from a multivariate normal distribution with a certain distance-based correlation structure that was derived by conditioning on the black dots. So the black dots are my 8 realizations of sine of x, of my expensive computer model, if you will. And you can see how these random functions interpolate the data. They go through the training data locations, and they have a sensible spread away from the training data locations. You'll hear people talk about the football shape. If you're North American, we talk about the football shape of these predictive intervals because they look like American footballs. If you're not North American, you might talk about the sausage shape. It kind of looks like a sausage. It has a quadratic expansion of uncertainty away from the training data inputs. And it's great for connecting the dots and quantifying uncertainty and so on. So this is why people like them, like Gaussian processes for computer simulation experiments. You can get really fancy with this. I made a very simple Euclidean distance-based correlation structure. If you want to do something else, you can put almost anything in as a covariance function, as long as you can show that it generates a positive, definite covariance structure. Here I've created a slightly more general version of that correlation function where I've got a scale parameter nu, so I can deal with functions on multiple scales. And I've got a white noise parameter tau, so I can break interpolation, so I can handle noisy data and smooth that noisy data. And I've introduced what are called length scales theta that allow the rate of decay of correlation to differ in different input directions. We call these hyperparameters. They're really just ordinary parameters, but we like to emphasize that the Gaussian process is a non-parametric model and gets its flexibility from pairwise distances and through hyperparameters like these extra ones that I have introduced as kind of a secondary wave, if you will. But the way that we perform inference for these unknown parameters is the same as we would for any other parameters. We could use the likelihood, which is what I'm going to show you. I'm going to take the MLE, but you could do Bayes, you could do cross-validation, you could set them through other means, I suppose, maybe moments. So here I've written down a log likelihood that you might get from an ordinary multivariate normal distribution, and I'm differentiating it with respect to one of the parameters, with respect to this scale parameter nu, and solving for its MLE in closed form. So you can do that for that new parameter, but you can't do that for the other parameters. You can differentiate, but you can't solve in closed form. So on the next slide, I've written down what's called the concentrated log likelihood. I plugged in nu hat and written down the likelihood as a function of the remaining 2 sets of parameters and used the chain rule through matrix derivatives in order to express the derivative of the log likelihood. And again, you can't solve analytically. You can't set to 0 and get closed form solutions, but you can do Newton-based methods. Those work really well. And that's what I'm going to code up for you on the next few slides. This is a slide of all code, right? Obviously, the point isn't to read this, but I've written down a negative log likelihood function as a function of parameters and the data, and I've written a gradient of the negative log likelihood function, again, as a function of parameters in the data. And then I can plug that objective and derivative into my favorite optimizer. So here, on the next slide, I'm just going to shove it into the optim function in R after I generate a data set for the purpose of illustration. So we did a one-dimensional sinusoid before. The input dimension is not really a factor. All you have to do is be able to calculate pairwise distances. So here I'm going to illustrate in 2D. I can still make pictures in 2D, so maybe that's why people prefer 1D and 2D, but there's really no input dimension restriction. Here the function is a nonlinear function of x1 and x2, and we'll get to see what it looks like in a second. There are 3 hyperparameters, 2 length scales, 1 in each input direction, and 1, this is called the nugget parameter, 1 white noise variance parameter that comes out of my optimizer. And then I need to take those parameters and plug them into my predictive equations. So on the next slide, I'm really just cutting and pasting from code that we had earlier on a new predictive grid with the parameters that I got out of my optimizer. And then I can draw on the next slide from the predictive equations and visualize them for you. So here on the left, I'm showing the mean surface that I estimated as a function of these two input dimensions with the data set comprised of about, I think there are 40 training data locations. And those are shown as open circles on the right, and the surface on the right is the standard deviation surface. And you can see that it has properties that are similar to the sausages that we saw earlier. The variance is low nearby the training data and high away from the training data. And this is in spite of there being noise in the data. I should have pointed that out earlier, but if I go back a couple slides, you can see that I'm adding a small amount of noise to my Y values here. So it's smoothing out our training data and giving us nice predictions with sensible uncertainty quantification. All right, so there's your Gaussian process surrogate modeling review. Where do we go from here? What am I really going to talk to you about today? So increasingly, data in geostatistics and machine learning and computer simulation experiments, which all involve Gaussian processes, are becoming more challenging to work with. In particular, I'm going to focus on regimes where the signal to noise ratio in the data is low and possibly changing over the input space. So I care about stochastic computer simulators. My favorite come from epidemiology. You imagine that in some configurations, you could end up killing everybody, and in other configurations, everybody survives. And then in between, there's a lot of uncertainty about what happens. By luck, you could end up with an epidemic that blows out of proportion, or you could end up with everyone being fine in the end. All right, so what goes without saying in that context? If you have noise, then you probably need more data, right? The noisier your data is, the bigger your computer experiment will have to be in order to separate signal from noise. But if you've been looking closely at the math on the previous slides, you'll notice that we're dealing with an n by n matrix, and we need to decompose it. To get predictions, we need the inverse, and to evaluate the likelihood, we need the inverse and the determinant. And unless we build in some special structure, that's going to have a qubit cost, which is really going to limit the size of the training data that we're going to be able to work with. So what can be done? Well, in the computer experiments world, we have the luxury of a great deal of control over the design of that experiment. And an important feature that you want to build into that design, I'm going to argue over the next few slides, is replication. So by replication, I mean repeatedly observing simulations under the same conditions. So getting multiple Ys at identical X's. Okay. So maybe something that you learn in Stats 101, if you go over repeated sampling, is that replication can be a powerful device for separating signal from noise. And what I'm going to show you is that in the Gaussian process context, it also gives a substantial computational savings. So here I'm introducing some new notation. I was using capital N previously to represent the training data size, but now I'm going to observe that data at little n unique input locations. And I'm thinking here that little n will be a lot smaller than big N, or I'll have many replicates at a smaller number of unique input locations. It turns out that a common linear algebra trick called the Woodbury identity can be used to show that with Gaussian processes, you only have order little n sufficient statistics rather than order big N sufficient statistics if those big N represent replicates at little n input locations. And in other words, you can build the predictive surfaces by decomposing little n matrices rather than big N matrices. Or I should say little n by little n and big N by big N. And basically what you're doing here is you're replacing the individual observations with their averages at the unique input locations. That oversimplifies a little bit because there's actually more sufficient statistics than that, but that's the crux of it. And that's been known as stochastic Kriging for about a decade, although it was an asymptotic result 10 years ago. But we've shown that there's actually an identity involved. So you get exactly the same predictive equations under this Woodbury trick as you would under a full N calculation. So what that leads you to is little n cubed calculation rather than big N cubed calculation. Still cubic, but cubic potentially in a much smaller number. And I'm going to try to convince you that this is a substantial result by going through one more slide of math and then doing an illustration. You can play the same trick as I showed for the predictive equations on the previous slide. You can play that same trick with the log likelihood and its derivatives. So you can shove the whole framework into your favorite optimizer to learn any unknown hyperparameters and then get predictions relatively quickly. So let's illustrate that. I'm going to go back to the 2D problem that we worked with earlier. So same test function, but I'm going to train it on a much larger data set. It's going to have 100 unique inputs in that two-dimensional space, but I'm going to expand that out through replication by taking a random number of replicates for each unique input location. So it's just uniform from one unique observation to 50 total replicates. So I'm going to get about 2,500 size training data set on average. And the code here is building that training data set. Again, I don't want to go through it line by line, but it's doing it. And then I'm going to, instead of cutting and pasting, which is what we were doing before, I'm going to use a library that is developed specifically to work with this Woodbury trick and to give us fast estimates. So the library is called hetgp, and I'll explain where the het comes from in a few slides. The right way to use the code here is with the MLE command on a homoskedastic Gaussian process with the training data and some parameters that describe how inference is going to be done. There's also a way to use it to kind of cripple it from using the Woodbury trick. So this will use the Woodbury trick by default, but if I don't want it to use the Woodbury trick, I can tell it not to in a kind of convoluted way. And you wouldn't ordinarily do that, but for the purpose of a comparison, I'm doing that now to show you how substantial the differences in compute time are. You get the same answers, more or less. The optimizer doesn't work exactly the same way in both cases, but you get almost the same estimates for the unknown parameters, but you get them in many orders of magnitude faster if you use this linear algebra trick. I don't know what that is, 1, 2, 3, 4 orders of magnitude faster. That's substantial. Several minutes down to less than a second. All right. So that's cool. Replication is great for separating signal from noise. And it also gives us computational savings for Gaussian process surrogate modeling. So we can handle bigger data sets and therefore more noise. But what about if the noise level isn't constant? What if the noise level is changing just the same as the mean is changing? What if it's changing non-linearly? Or what if there's input-dependent noise? So here's the Greek word for that. Heteroskedasticity means input-dependent noise. This is my favorite test example illustrating the challenges involved in input-dependent noise settings for Gaussian processes. This is the motorcycle accident data. It's actually a computer simulation. So it was a computer simulation done in the 80s that measured the acceleration of the helmet of a motorcycle rider as a function of time before and after an impact. So you can kind of imagine where the impact may have been here at maybe time 15 or something like that. There's very low acceleration, and then something happened, there was an accident, and then there's a whiplash, and it's a noisy simulation. There is a degree of replication built into this data for reasons that I explained earlier, to separate signal from noise. But you can see that the Gaussian process, which I fit to this data the old-fashioned way as an ordinary homoskedastic Gaussian process, captures the mean behavior well, but it doesn't capture the variance regimes well. It doesn't get that there's low noise for low times and higher noise for medium times and lower noise again, but maybe not quite as low for the higher times. How can we deal with that? Well, a great idea came actually even longer ago than the replication ideas that I just told you about from the machine learning literature. So machine learners were worried about heteroskedasticity in the late 90s. And this is a great NIPS paper from 1998, where they put together a latent variable structure and gave those latent variables, which they interpreted as variances or log variances, they gave it a Gaussian process prior. So they were putting two things under a Gaussian process prior. They were putting the mean, which is the old school way of doing it, and the variance or the log variance under Gaussian process priors. And then they would try to learn those latent variances alongside of the latent mean structure. And they did that with MCMC, which meant that it was completely impractical, especially back in 1998. But even today, doing a full MCMC with data augmentation and so on to learn potentially many latent variables is not computationally tractable, except for very small numbers of unique inputs, n. But the idea is still a good idea. And what we did is not super brilliant, but it hadn't been done before, I think, is that we put this latent variable framework inside the Woodbury MLE framework so that you were working with only unique input locations, which is important for latent variance identifiability and also for computational tractability. And we worked out what the derivatives of the log likelihood would be as a function of those latent variables and shoved them into an optimizer. And we're very pleased to find that the optimizer worked really well. So this is a very well-behaved objective surface, even though it is potentially in very high dimension if you have a large set of unique training data examples. So let me show you that in action. I don't want to do too much math on this because I want to move on to other things. But here I'm going to put this motorcycle accident data into the flagship function of the HET-GP package. So this is to work with MLEs of heteroskedastic Gaussian processes with the X's and Y's from the motorcycle data. And even though the motorcycle data has hundreds of training data locations, I can learn hundreds of latent variances in less than a second. And then I can make predictions for you, which are shown on the next slide. So on the left, I have my updated predictive surface that's heteroskedastic. It learns the low noise region and the high noise region and the middle noise region as we move from left to right. And in the right panel, I'm showing you a pure look at the variance alongside independent variance calculations that are done for replicates. So each one of these green dots represents an S-squared calculation of variance at locations where we have repeated observations. And the point is just to show you how variance is being smoothed here. So this is the smoothed Gaussian process estimate of variance as we track from left to right in the input space. All right, so let's do some real examples. Everything's been pretty toy so far, although the motorcycle example is technically a real example. It's a pretty old one and a pretty simple one. So I said epidemiology is a big application area. Here's an epidemics example involving an SIR model, a susceptible infected recovered model. This is the simplest version of such models, but they can involve a substantial amount of stochastic dynamic programming to solve. We've also done this with Ebola models using social networks and so on, but that's too involved to explain in the talk today. So there's a simulator that was developed by a colleague of mine that takes a 2D input vector. So this is an initial number of susceptible individuals and an initial number of infected individuals. So we're seeding a population with a disease and then watching it spread by some dynamics and the resulting surface. So what we're going to study is how many infected individuals there are at the end of the simulation. And it turns out that that's nonlinear and it's also heteroskedastic. And there are some very high noise regions. So I'm just going to run this SIR computer code, which is built into the HET-GP package. So we provide the simulator so you can do this example. I'm going to train it at 200 unique S and I naught values in the input space with a random amount of replication on each so that the training data size is relatively big. So this is almost 10,000 runs of the simulator. And I'm going to fit my heteroskedastic Gaussian process by giving it those XY pairs. And it takes a little longer than our previous examples. Whoops, I went ahead accidentally. It takes a little longer, but still only takes about 3 seconds, which is tremendous for Gaussian processes being trained on 10,000 runs. And then I'm going to predict on a grid and show you what the mean surface and the standard deviation surface looks like on the next slide. So the training data sites are the open circles on these heat plots, and the left heat plot is the mean surface, which is relatively simple. It's got kind of a, it looks linear, but actually it's exponentially increasing as we move along this diagonal here, which makes sense. As you have more susceptible and infected individuals to start with, you have higher spread of the disease over a period of time. On the right is the standard deviation or the uncertainty surface, and you can see that that's more complicated. We have a variance surface that's more complicated than the mean surface. Apparently, a large number of susceptibles and a smallish number of infected individuals is the most uncertain regime as far as what the outcome of the simulation is. And it's kind of got a nonlinear relationship elsewhere. It decays in this kind of funny way as we move from right to left in the input space, particularly for the S input. All right, here's another example. I've got 3 examples for you. This one involves measuring the amount or the concentration of oxygen in water in the ocean, deep in the ocean. So there's a simulator that takes 4 input variables, and 2 of them are coordinates, so longitude and latitude. Where in the ocean are we talking about? And 2 of them are oxygen diffusion coefficients. And for 4 of these inputs, it'll tell you what it thinks the oxygen concentration is at that under those configurations. So I don't want to go too much into the details. You can get the code behind this from GitHub, and I wrote a little R wrapper so we could work with it. And here's just a kind of a picture of what we're dealing with. I want to show you that the simulator is heteroskedastic. So here I've fixed 3 of the 4 inputs, and I varied the longitude input to show you that the response surface is nonlinear. It has kind of this zigzag shape, and it's heteroskedastic. It has a low noise regime and a high noise regime, and then it's lower noise again. And in higher dimension, that's more complicated. So let's do some fitting. I'm going to deliberately use a poor choice of design, and I'm going to fix us to 2D here so we can make visuals, even though I've got versions of this in the full 4-dimensional space. I'm going to choose a poor design because the next segment of my talk is going to be how to design these experiments, and I'm going to build for myself a kind of weak straw man so I can knock it down later. Okay, so I'm going to do 25 unique locations with 20 replicates at each location, and then I'm going to fit my heteroskedastic Gaussian process, which is relatively quick, on these data, and plot for you what the mean surface and the standard deviation surface look like. So you can see that this maybe wasn't an ideal design, but I have learned a degree of nonlinearity in the mean, and I have learned an input-dependent variability in the standard deviation. Okay, before I transition the talk to design, I want to do one more quick example. This is a real simulator it's from inventory management called the Assemble to Order simulator, and it's 8-dimensional, which makes it very difficult to describe in detail quickly in this talk, so I'm not going to. But suffice it to say that our methods work really well on this data. They give better results. So here we're looking at proper scores, so higher is better. Our methods are in red in 3 different variations, and the other methods that we entertain have much lower and more highly variable scores. And the reason I'm bringing up this example is because I can extract out a version of this experiment from the HetGP package and show you that it involved 1,000 unique input locations and 5,000 or so total with replicates, and that I can recreate the score out of sample so I can compare to it later after I talk to you about how to design these experiments. So that helps me transition into the final segment of my talk. How do you design a simulation experiment when you think the mean and the variance are changing nonlinearly? I think you need to do that sequentially. Trying to design before you understand something about the response surface is fraught with all sorts of challenges. The designs that you might be able to create from a mathematical perspective are sensitive to things that you don't know, like hyperparameters or like latent variances. And I don't think that you can do it really unless you know good settings for those values, and you can't know good settings of those values until you've run a little experiment. So I think it makes sense to kind of build things up one at a time. Start with a small experiment, fit a model, choose subject to some criteria, what next run you want to do your computer model at, do that run, and augment your design and repeat. So I think this is a very sensible framework. I think it's easy to operationalize because the criteria are in many cases obvious. So if I want to minimize my predictive uncertainty, I might look at some aspect of predictive variance when choosing my next design point. And in fact, that's what I'm going to do. There are other things you might want to do. If you're interested in minimization, you might want a different criteria. If you're interested in finding level sets in your response surface, you may be interested in yet another criteria. But I'm going to look at predictive uncertainty. So a very common decision criteria for sequential design is what's called integrated mean squared prediction error. So the formula for that is here. I want to integrate over the entire input space my predictive variance as trained on the previous training data values and thinking about how it would change as a function of a new data location. And it turns out that that integral is available in closed form. This has been known for a while, but we worked out the details of this integral for our heteroskedastic Gaussian processes, and I put some math on the slide to convince you that that's true, but I'm not going to go through it. So it turns out you can evaluate integrated mean squared prediction error as a function of new input locations in closed form, and then you can put that criteria into your favorite optimizer, and you can give it closed form derivatives as well, and use that as the basis of sequential design. So before I do that, before I put that into a design framework, I want to kind of show you an interesting thing that you get from this integrated mean squared prediction error when the variance is not constant. So this is kind of a toy example where at these five red dots, think of those as input locations where I have data. So I know what the variance is at those locations, but I don't know what the variance is other places. And the green curve and the blue curve represent two different hypotheses about what the variance could be away from where I have a large degree of information about the variance. So think about away from my training data locations. I'm going to take these two variance hypotheses and I'm going to calculate integrated mean squared prediction error for them. So this function here codes up the math that was 2 slides back, so I can evaluate it as a function of a new location x and plot that for you under the two variance hypotheses that I had on the previous slide. So here is that plot. So the green curve and the blue curve are two different IMSPE surfaces under the two different variance hypotheses. And I want to minimize predictive uncertainty. So if I believe the blue hypothesis is correct, I want to choose an input here at about 0.3. And if I believe that the green hypothesis is correct, I want to choose one here. And it's interesting to note here that this is exactly at one of the input locations before. So this is representing a replicate. The green hypothesis says, I want a replicate. I want to know what y of x is at an x where I already have y values. So that's interesting. There are some noise surfaces that prefer replication, which is a result that was not previously known in the computer experiments literature, in part because people hadn't worked too much with stochastic simulations, and we worked it out. In fact, we did a little bit of math. My postdoc, Mikhail Benoit, was great at this. This is definitely not squarely in my wheelhouse. But he found that if your noise hypothesis, if what you believe about predictive variance is big enough, so this is a complicated expression, but the important thing is the inequality. So if your variance hypothesis is bigger than something, then you will choose a replicate if you're choosing by IMSPE. And I can plot this function for you. I've coded it up here just to show you what it looks like next to our variance hypotheses. So notice how the green line is everywhere above the gray line. The gray line is that threshold where I'd replicate. And in fact, they meet right here at this replicate. So if your belief about variance is everywhere high enough, then you will choose a replicate. Why? Well, because of that mathematical result, but more colloquially, because your uncertainty is high and replicates represent the most efficient way to help separate signal from noise. So it's a very intuitive result from that perspective. All right, how does this work in practice? I want to do a sequential design where variance is changing in the input space. So what we did was we tried to create a synthetic example that was a lot like the motorcycle example, in the sense that it had high noise and low noise and higher medium noise regions, but was an actual function, an actual computer simulator where we could generate outputs at whatever inputs we wanted. So this is the surface that we came up with, and we're going to pretend we don't know it and design an experiment for learning it and see where we get runs and where we get replicates of those runs. So here's how that design is going to go. I'm going to start with a small initial training data set. So I'm going to do just 10 initial runs in the input space and get a fit to those data, and then optimize IMSPE. Our IMSPE calculation does something called lookahead, which I haven't explained to you because it would be too much of a digression, but suffice it to say it's fancier than what I just explained to you. And I can then look at how the solution compares to what I had so far. So I had 10 to start with. These are the first 10. This is the 10th one here. The 11th one looks like it's somewhere between the first two. So it's in the high noise regime, and it is not a replicate. You can see it's not identical to any of the training data locations that we had so far. So I incorporate that run into the data and then update my fit. There's a nice update command that comes with the package that does quadratic calculations instead of cubic ones in order to update the fit. And then I can repeat. So I'm just going to repeat those two things, optimize IMSPE and update for a bunch more times until I get 500 samples. 500 is way overkill for this example, but it makes a nice picture. And I can show you that picture on the next slide. So here's my surface where I've learned that the variance is high here and that the function is nonlinear and the variance is lower there again and higher again. And the gray bars here are showing the degree of replication because it's a little hard to see in the open circles, showing you that at some locations like this one here, I have a very high degree of replication. All right, we've done this basic scheme, and I can see I only have a couple minutes left, so I'm going to go kind of quickly. We did this basic scheme on real examples. So here's the ocean oxygen example. I took the same for loop that we had 3 slides ago and applied it for the ocean simulator, and I can show you what we got. So visually, this is a much more attractive design. There are many more unique input locations than the simple Latin hypercube sample we had to start with. I've learned a much more nuanced mean surface and a much more nuanced variance surface. The coordinates of these numbers are the unique locations, and the numbers themselves are the degree of replication. So I had 9 replicates here where the variance was highest, which makes sense. You want to take replicates where they're going to help you reduce uncertainty. And in fact, if you look at the swath of numbers in this high variance region here, I've got lots of 7s and 6s and 4s, and I have fewer of those outside in the red region. So I've concentrated my replication where it's most valuable, where variance is high. If you repeat that over and over again, randomizing over initial locations, you can make comparisons to other methods. We did that. This is not a reproducible part of the talk. It was done offline. I get the best RMSEs out of sample when I do things heteroskedastically and sequentially compared to homoskedastically or not sequentially. And I also get the best scores out of sample. I don't want to go too much into this, but suffice it to say that that one example I showed you, which was reproducible a slide ago, is the general trend when you repeat it over and over again. We did the assemble to order problem. This was the 8D problem that I didn't go too much into. We did things in one shot with 1,000 unique locations, but high replication. So this is about 5 replicates per point. And we did it adaptively with the sequential design with about the same number of unique locations, but many fewer replicates. We didn't choose how many replicates there would be among the initial N, but the IMSPE found that for us. And the result is, if we make a comparison based on score, that the adaptive one is better than the non-adaptive one. So we had 2/5 of the size of the computer experiment. So we saved a lot on simulation, but ended up with a predictor that was more accurate and gave better uncertainty quantification. All right, last 2 slides. Let me tell you what I told you. When the mean and variance are changing non-linearly in the input space, it's still possible to get accurate fits with Gaussian processes by using a Gaussian process for the mean coupled with a Gaussian process for the variance. When you're designing experiments, you want to have replicates so you can separate signal from noise. The more heteroskedasticity and the higher the noise, the more replication you need. And I think that's intuitive. Everything that I've shown you is in the package, and there's a vignette that goes with that package that has reproducible code, a lot like the code that I showed you in this talk. And in fact, if you'll let me end on a plug, I have a new textbook that is written in exactly the same way. So this is all about Gaussian process regression and other downstream applications like sensitivity analysis and optimization and heteroskedastic modeling. And you can buy it from CRC if you want, and the money for that will go into my beer fund, or you can get it for free from my webpage in our Markdown. It's fully reproducible, or as a PDF. So let me end there, and thank you guys for listening and for the invitation. I had a great time.
Thank you very much, Bobby, for this excellent presentation. Now I'm looking at Hoover for some questions. There's the question answer section or the chat possibility. I would encourage people to ask some question. Probably I could start with a short question. You mentioned at the end that the adaptive design was more accurate than the batch design, but wouldn't that also depend on the way how you design the batch, on the size, etc.?
Sure, yeah. It's always important how you choose your comparators. There is probably a batch design out there that would beat the adaptive design, and if you knew what that is, so if you had a lot of prior information, you could definitely make things go the other way. I guess maybe that's my answer. In general, I think it's hard to know what that design would be.
Okay. People could also ask questions directly. David, I think.
Yes, I had a quick question. Well, two. First of all, I'm delighted to see this book is out here. That's great, Bobby, and you'll get your beer money out of this. Second, the Woodbury trick. I assume that's related to the Sherman-Morrison-Woodbury theorem.
It's almost the same. So the Sherman-Morrison-Woodbury is like the rank 1 version, and this is like a slightly more general than that.
Thank you. Great.
Another issue, you mentioned this integrated mean squared prediction error. I think this is quite common, but it also makes technically things quite straightforward in your case. Is that right?
That's right, yeah. There are some other criteria which are similarly tractable analytically. You can do what's called expected improvement. People do that when they want to optimize find the x's that minimize f of x. You can do the same thing with contours. So there are a limited number of these heuristics or statistics that are available in closed form, and others you can get by Monte Carlo.
Okay. Mm-hmm. Are there any further questions?
Yes, this is Pulong. I have a question. So you mentioned about replication. So, and this helps in detecting the changes in the mean and variances. What happened if we have changes in the covariance structure, does this strategy still works?
Good question. Yeah. So all three of those things that you mentioned, so changes in the variance, changes in the mean, changes in other things about the covariance structure, those are all called non-stationary modeling structures. If you have something that's changing in the input space regarding that covariance, then that's much more difficult to model. And it turns out that variances, in this case, are among the easiest to cope with. So you can deal with non-stationarity in the variance, or more simply heteroskedasticity with the framework that I showed you. But more to your question, if you have more subtle changes to covariance in the input space, that can be much harder. And there are methods that target that, but I think that's mostly an open area. People talk about deep Gaussian processes as being potentially valuable, and I know you've done some work on that, and I'm very excited about that area. If you do this idea, this heteroskedastic Gaussian process idea, when you have general non-stationary dynamics, then you still get decent fits and you get decent sequential designs based on variance, but I don't think it's as good as you could get with a more direct approach. It's better than if you didn't acknowledge it at all, but I think you could do even better with something fancier, and I'm excited about some of the developments that are coming online for that.
Okay, thank you.
Any other question? You can simply unmute yourself. Well, if there are no further questions, let me thank you again, Bobby, for this nice presentation. And it was really great having you on board at this conference. Thank you very much.
Thank you.
We see each other or hear each other in a couple of minutes. Thank you very much.
Sounds good.